Silicon Photonics and Heterogeneous Integration Challenges. This is AMD's MCP that combines a GPU with in-package memory, HBM Gen 1. This is a more recent example of an MCP being the third generation Threadripper. But it's not just AMD. NVIDIA has a history of MCPs, the most recent being the NVIDIA Ampere released last month. Our final example is a Xilinx FPGA that couples a FPGA with in-package memory. So what can we conclude from these examples? Well, the MCPs require significant packaging technology, so they must provide significant benefits to the developers. However, you might wonder if there are any additional constraints for systems such as these. Let's consider HBM and see if there is anything we can learn from that example. This is the JEDEC spec that governs HBM. The question is how one should integrate HBM into the package. This diagram shows HBM on the left and the LCC on the right. Note that the HBM die stack has direct connections to the package substrate BGA. These connections are more than just VDD and VSS. They also include the so-called DA or direct access port. The configuration shown requires 98 I/O pins, which must be supplied by the package. And while they are beneficial, allowing the memory vendor direct access to the die for bring up and RMA purposes, they nevertheless do provide an additional constraint for the package. Specifically, they require precious BGA balls to be deployed to support the HBM die. Additionally, while it is not obvious, HBM form factor, essentially the die size, is another constraint that impacts package design. Not only the substrate and poser designs are impacted, but even potentially the SoC design itself, specifically the precise locations of the PHY. These are merely examples of how heterogeneous integration places additional constraints on the package design. The question is, what are the additional constraints that might be incurred because of in-package photonics? Before we discuss those, let's motivate the purpose and need for in-package photonics. This is a chart developed by Gordon Keeler at DARPA. The specifics of the chart are not important for this discussion, but suffice it to say that the y-axis is a figure of merit for interconnect performance, whereas the x-axis represents interconnect distance. Note that in-package and onboard communication is all electrical and is limited to a distinct trend line with lower performance as the distance increases. However, once you go off-board, the performance is discontinuous and substantially lower. DARPA wants to improve the off-board interconnect performance. In fact, DARPA would like to see roughly 4 orders of magnitude improvement. How can this be achieved? The answer is in-package photonics. At Ayar Labs, we have been commercializing DARPA-funded silicon photonic technology that we call TerraPHY. The development of any new technology is multifaceted, but for the purposes of this talk, let us consider 3 separate development areas. Those are: first, devices, including modulators, detectors, and waveguides. And second, designs, including drivers, TIA, and associated logic. And finally, the third, assembly and test. In fact, the focus of this talk is on assembly and test, and more specifically, how materials engineering can impact the cost and performance of the final product. Note that many believe that assembly and test comprise approximately 75 to 80% of the cost of goods sold, or COGS, for silicon photonics products. Therefore, this is an excellent place to focus, particularly for this conference. Ayar Labs, in collaboration with Intel, has already demonstrated TerraPHY in-package photonics integrated into an advanced MCP. The upper right image shows an MCP with a Stratix 10 co-packaged with 2 TerraPHY die. The package utilizes Intel's EMIB substrate, a diagram of which can be seen in the lower right. The middle image is an isometric SEM image of the mixed pitch copper pillar technology used for this package. Finally, the image to the left is an optical micrograph of the same die, clearly showing 2 regions of copper pillar. The dense region supports AIB, a high-density electrical PHY, whereas the rest of the die supports the optical macros. We have discussed examples of leading-edge MCPs and how systems can benefit from in-package photonics. but the commercialization of revolutionary technologies usually poses new and unique challenges. It is useful to consider 4 distinct development areas for in-package photonics. First, there is the platform. When I say platform, I mean the package form factor, bump structure, and fiber attach approach. Second, there is test. Test includes wafer sort as well as final test. Third, there is fiber and fiber components. Optical fiber was first widely deployed for long-haul systems, and hence it has been optimized for that application. Finally, the fourth is the ecosystem, which is the combination of all of the stakeholders. Let's start with the platform. There are a lot of assumptions that go into package design, but for the sake of brevity, let us focus on, first, the copper pillar, which is required due to the high-density interconnect used for in-package communication between the SoC and the teraPHY. And second, fiber attach, which was required to couple the on-die photonics to fibers, which are then routed to other systems. But before we can discuss the materials engineering opportunities, we must first understand the basic structure of a stereotypical teraPHY die. This is an isometric scaled drawing of a singulated teraPHY die, roughly 8 mm on a side. 55 micron pitch copper pillars can be seen in the upper right section of the die, while 130 micron pitch copper pillars can be seen in the center of the die. Note that this combination of copper pillar pitches is not a limitation of teraPHY. Rather, it is a great example of how teraPHY can be adapted to different packaging form factors. This particular copper pillar pitch is perfect for Intel's EMIB substrate. However, different copper pillar pitches and requirements could be implemented for other package form factors. Regardless, on the lower left edge is the so-called Vgroove array. For this example, there are 12 Vgrooves in which 12 optical fibers will be mated. Adjacent to the Vgrooves is a region of the die called a spot size converter. More on that later. This is a zoomed-in view of the same die. The Vgrooves are displayed prominently in the center of the image, and there is one spot size converter for each Vgroove. Let's take a cross-section of the same die, bisecting one of the Vgroove spot size converter pairs. It is clear from this image that the Vgroove is etched into the silicon die. What is also clear is that the spot size converter has an undercut etch below it as well. In other words, the spot size converter is cantilevered over the undercut region. Let's zoom in further to the Vgroove region. From this vantage, we note how the spot size converter bridges the undercut region. Here, I have inserted a single fiber to show how the fiber couples to the chip. In practice, all of the Vgrooves would contain one fiber, but for clarity, I have only shown one here. The optical fiber is a standard single-mode fiber, with a mode field diameter of around 8.5 microns. Light propagating down the fiber is incident on the optical facet. Here I have shown the location of the optical facet for the adjoining Vgroove. However, this same structure exists at the end of each spot size converter. Now we can start to consider some material properties for the assembly. First, note that there is a slight gap between the optical fiber and the spot size converter. This gap, in fact the entire region, will be filled with an epoxy. The packaging industry is used to material selection, and advanced materials exist that control alkali contamination, Young's modulus, coefficient of thermal expansion, adhesion strength, etc. However, here the epoxy will be part of the optical path, and therefore we must consider the optical properties of the material as well. For example, we are interested in the index of refraction and absorption of the epoxy. Additionally, it is common to add fillers to epoxy to control the material properties, but fillers here might cause photon scattering and hence are discouraged. So the selection of the epoxy is important, not only for the physical integrity of this fiber attach, but also for the optical performance of the same structure. Speaking of physical integrity, note that the fiber will be epoxied into the Vgroove. Therefore, the adhesion between the optical fiber, Vgroove, and the epoxy itself is very important. As the wafer is processed through the die prep and flip chip steps, it is important to keep the Vgroove region clean. For example, the region, including the spot size converter, needs to either remain clean or to be cleaned after dicing. Additionally, if flux is used during the flip chip process, The flux should not contaminate the optical facet. Finally, it is important to avoid filling this region during the capillary underfill process. This includes either epoxy bleed out or outgassing of the epoxy. Let's view the edge of the die on the side with the V-grooves. The inset shows a zoomed-in view of a single V-groove. Note the trapezoidal shape of the slot. Now let's place a fiber into the V-groove. From this view, note that the center of the fiber, the so-called core of the fiber, which is where the light propagates, is vertically aligned to the chip based on the position of the V-groove. In the inset figure, note that the fiber is surrounded by adhesive. This is the same aforementioned adhesive that both secures a fiber to the V-groove while also participating in the optical performance of the coupling. Given the proximity of the spot size converter, the adhesive will also fill that region as well. Therefore, it will be important to control the adhesive's viscosity and propensity for capillary flow. Finally, note that while the die is hermetic, as all CMOS die are, the epoxy is exposed to environmental stress. For example, epoxy must perform under highly accelerated stress testing, HAST, temperature humidity bias, THB, temp cycling, and moisture sensitivity level testing. Ideally, the epoxy will not hygroscopically swell, since the fiber must be precisely held in position relative to the spot size converter. These are some of the general examples of material properties that should be considered for fiber attach applications. Now let us switch to another component of the MCP, the copper pillar. Here we see copper pillars that have been fabricated on Ayar Labs Terrify die. Note that the mixed bump pitch design in the left image, the 55 micron pitch copper pillar in the center image, and a zoomed in view of a single 30 micron diameter copper pillar on the right. These structures are integral to a 2.5D assembly, particularly given the high density requirements of advanced interconnects such as AIB. The fabrication of copper pillars onto a V-groove enabled wafer is beyond the scope of this talk. However, it is important to note that the topology created by the V-grooves will affect traditional photoresist applications, such as spin coating. Alternative approaches will have to be pursued. Additionally, when plating either for the underbump metallization or the copper pillar itself, one must not contaminate the V-grooves or the spot size converter. Metals will cause a very high absorption and will severely impact the performance of the fiber attach process. Therefore, it is an opportunity for materials and process development to create high-volume manufacturable copper pillars on V-groove-enabled silicon photonic wafers. Finally, we can discuss the basic form factor of the 2.5D in-package silicon photonic MCP. Note the modified organic substrate, or high-density buildup, that allows the insertion of a fiber array adjacent to and interacting with the Terrify die. Additionally, it becomes apparent that one must control the capillary underfill, or CUF, process as discussed before. The same is true of any material used in the assembly, including but not limited to the polymer thermal interface material, or PTIM. Finally, note that this system assumes that the fiber is permanently attached to the die. If this assembly is soldered to a printed circuit board, then we will need to consider the performance of the entire assembly at reflow temperatures. This is a topic for the next section. Before we discuss fibers, let's review the material considerations for what we have called the platform. Starting with copper pillars, we need processes and materials that enable copper pillar fabrication on V-groove-enabled wafers. This includes photoresist technology that can deal with high topology surface, plating technology that prevents contamination of the V-groove and spot size converter region, and cleans if necessary to ensure good performance of the fiber coupling. For solder and flip chip, MCPs can benefit from low temperature solder, a process that will be explored in more detail later. Fluxless flip chip or effective flux cleans for the optical facet, and potentially any required cleans post flip chip. Finally, regarding the polymer selection, the underfill technology cannot have epoxy bleed out or outgassing that fouls the optics. And any selected polymer must include appropriate optical properties to go along with the traditional mechanical properties. Now let us consider a test. Heterogeneous integration requires known good die. In the MCP shown, there are 5 CMOS die, 1 SoC, and 4 Terafy dies. And any test escapes that fail one of these dies would be costly. Not only would you lose that die, but you would also lose 4 others, not to mention the interposer and the substrate. Therefore, known good die is extremely important for the MCP success. However, while the industry routinely performs wafer sort on mixed signal wafers, here we have the monolithic integration of CMOS and silicon photonics. Therefore, the challenge is how to enable electro-optic wafer sort to guarantee known good die. Here is a simplified assembly and test process flow with 2 branches. The top branch is typical for an SoC die. The wafer leaves the foundry, is tested at wafer sort, and then enters die prep. For the purposes of this discussion, die prep includes copper pillar, back grind if needed, and singulation. The lower branch is the silicon photonic branch. Here, wafer sort is shown as electro-optic wafer sort. Since Terafy is monolithically integrated, the die requires wafer sort testing that is similar to other highly integrated VLSI products. However, in addition, the wafer prober and probe card need to enable optical fibers to be aligned to the grating couplers. This allows photonic transceivers to be tested, improving test coverage, and thereby reducing test escapes. Therein is the challenge. As a very complex CMOS device, the die requires hundreds of probe pads, ideally greater than 300, which have to share the same space with up to 24 optical fibers. Current approaches use modified cantilever probe cards, which limits the number of probe pads. Additionally, to reduce the reliance on guard banding, it is ideal to test the wafer at the maximum operating temperature. For high-performance MCPs, it's not uncommon to operate the die with a junction temperature of 100 degrees C, sometimes higher. Therefore, it is safest from a guard banding perspective to test the wafer at 100 degrees C. However, this is currently not possible, given the temperature limitations of fiber arrays and probe cards. This is another opportunity for improved products, ostensibly based on advanced materials engineering. Let us also consider final test, which is less of a materials issue, but will nevertheless require adaptation. Note that the MCPs will have photonic components at this stage. If the MCPs has MT ferrules, then the module handler will have to require some interface with these ferrules to include a complete final test. In closing, KGD is a requirement for successful MCP integration. And to achieve that, we need electro-optic wafer sort that ideally supports 300 plus probe pins, up to 24 precision aligned fibers, roughly plus or minus 1 micron, and all running at 100 degrees C or more. And finally, final tests must be adapted to allow for post-fiber attached testing, ensuring that parts meet specifications before reaching finished goods. With signal attenuation of less than 1 dB per kilometer, optical fiber enables efficient point-to-point communication. Here is a concept image of how one could integrate a silicon photonic MCP onto a printed circuit board. Note that traditionally the PCB provides physical support, power, and input-output connections to the board components. Optical fiber provides a similar role, routing laser power from the external laser to the Terafy and the MCP, and routing signals to and from the MCP itself. Similar approaches have been taken using so-called flyover assemblies for high-speed electrical links. But are there options for optimization? First, consider the printed circuit board and the fiber itself. Real systems are more congested than what is shown here. Potential applications require multiple modules, DIMM cards, heat sinks, fans, etc. The optical fiber needs to be securely routed around these obstacles without getting damaged or blocking airflow. We should also consider the size and form factor of the fiber components, such as ferrules and ferrule connectors. Finally, any MCP that is comprised of fiber or fiber components should be reflow compatible. This enables the MCP to be soldered to the printed circuit board, resulting in both cost and performance benefits. To understand basic fiber routing, consider the Terafy Stratix 10 MCP shown earlier. We can route CW or carrier wave laser light to the MCP using optical fibers and MT ferrules, as well as connect the transceivers from the MCP to other systems. Note that the so-called fiber shuffle does not need to be reflow compatible. However, if the fiber arrays that are affixed to the MCP are reflow compatible, then the MCP could be soldered to the printed circuit board. Alternatively, one could use a socket for the MCP. What is the standard reflow profile? This is an example thermal profile as defined by the IPC and JEDEC. Note that the profile has an initial soak period with a final peak temperature at 260 degrees C. Note that the process is relatively short, with the room temperature to peak temperature time not to exceed 8 minutes. This profile is suitable for leadless solders. However, the industry has also developed so-called low temperature solders, many of which have a liquidous temperature below 200 degrees C. Materials and process development of these solders are very interesting for applications such as in-package photonics. Let's focus on the fiber components within the package. The fiber typically has a silicon dioxide cladding with a diameter of 125 microns. The core is a doped oxide with a diameter similar to that of the mode field diameter, again roughly 8.5 microns in diameter for the O band. The fiber is coated with a polymer which protects the silica fiber. For the purposes of this talk, it is the coating that is most interesting from a materials engineering perspective. The other consideration is the fiber ferrule and how to connect it to other ferrules. The typical acrylate coating is only rated for a maximum operating temperature of 85 degrees C. Here we see a datasheet excerpt from a common optical fiber. Fiber vendors have engineered higher operating temperature coatings, including both acrylates as well as polyimides. The challenge with polyimides is stripping. Polyimide is such a good material that it's hard to strip from the fiber, a process that is required for some assembly steps. Fiber connectors are another area of potential development. Fiber connectors are a high-performance and well-developed technology. However, they were developed for a central office environment. Let's start with the fiber ferrule, called a mechanical transfer or MT ferrule. It's typically fabricated from a thermoplastic. Currently, the glass transition temperature of this material is around 120 degrees C, which could result in stress relaxation, and in other words creep, during the reflow process. Different material formulations or types can improve the thermal stability of these assemblies. Additionally, as the number of optical waveguides going to and from the MCP increases, we will need higher density ferrule technology. This brings us to the final consideration, which is the overall silicon photonic ecosystem. The technology has some great promise, and simply due to limited alternatives, it will be deployed. But it will take an ecosystem to succeed. This includes design automation, availability of qualified wafer process nodes, to advanced packaging considerations such as copper pillar or hybrid bonding, material selection, and a robust and open assembly and test community. Material science and engineering will play a key part in this development.